So in this video, we're going to take a look at this GPA, ACT, IQ, percentile rank data set that we've seen before. I've already pulled in the data, and I'm just going to call the data file data. I've given it those names: GPA, ACT, IQ, perc rank, or percentile rank, and attach the data set. Take a quick peek at it. The idea is maybe you want to try to predict first year university GPA for college students based on their ACT score, IQ score, or some kind of intelligence test. I call it IQ, and their high school percentile rank. Okay, so first thing I'm going to do is I'm going to build a linear model. And I'll call it ACT IQ because I'm just going to use ACT score and IQ to try to predict that GPA. Okay. Next, I'll also build linear models. I'll build a linear model for ACT and percentile rank, and I'll call it this. Okay. And I'll also get a linear model for IQ based on IQ and percentile rank. In each case, I'm trying to predict the first year college GPA, but I'm using two different variables each time. The reason is I can't make a nice picture or movie, or I mean, I guess you'd have to do it with a movie, but I don't know how to make a nice movie or picture of four variables. Okay, but I know that I can use that RGL command to make 3D pictures where you have 1, 2, 3 variables, and check out so that we can look at GPA versus 2 variables at a time. Okay, so let's take a look at the output for each one of those models. So for the ACT and IQ model, it looks like the multiple R squared value is about 64%, and the looks like the IQ coefficient is significantly different from 0, and so is the intercept. We could probably, looks like the ACT score is probably not having a huge effect, at least not compared to IQ. When I look at the output for the second model, our R squared value is only like 14.97%. It's dropped considerably. ACT is no longer a or was it? I guess it wasn't significant in the previous model either. Its p-value is smaller, but still indicating that ACT is probably not a good indicator for the GPA in college. Let's take a look at the last output. If I try to model GPA versus IQ and percentile rank. Okay, so this model is indicating IQ is probably significant. Our multiple R squared value, or just R squared value, is almost 65%, 65%. Okay, so let's load in that library, that RGL library, and like I did in one of the previous videos, I'm going to set things up so that I can make several graphs at once. This WGL2 just indicates that this is my second window that I happen to have open, so you can ignore that. But yeah, so when you have this shared mouse equals true, it means that when you go to rotate one of the plots in that graph, that they will all rotate at the same time. That's kind of nice if you want to be able to do that. Now what I'm going to do is I'm going to plot all these three surfaces, which model GPA versus, say, ACT and IQ, or GPA versus two other variables. Okay, like so. Okay, so and let's go ahead and give this a title. I'll call this data. Okay, and so you can see that this is a plot of our actual data. Okay, I'm looking at the GPA and the IQ and the ACT variables. Remember, again, we want to think of our GPA as the response, so I'll try to keep it kind of vertical. And you can see there that, in fact, it looks to me like maybe sort of a planar model might be okay. If you look at the data this way, you can see sort of how a plane might sort of slice right through those data points, kind of going down through that way. And so maybe that's kind of how that model would. So next, let's make a model where we plot the output of that ACT and IQ model, where our versus ACT and IQ. Okay, and so this is so these are our data points. Okay. And I'm leaving off that fourth variable, right, because I don't know how to visualize or tell R to even visualize another a variable there. We can only do 3 variables at a time, unless we make a movie, right, and have this stuff change through time and let that other variable react as time, sort of. But this is our model over here. In fact, I should probably label it like that. I'll call it model fits. Okay, those are our fits. So you can see that that's what the fits are doing. The fits sort of outline the actual linear model. They sit right in a plane, right? Sort of a subspace of the 3 space. They sort of slice right through there, like what we were talking about. You see that? And so then, if you could superimpose these points on top of this plane here, you would see that, in fact, what you'd be looking at is, if I turn it this way, these points, how they jump off in the vertical direction, those would be our residuals, right? Okay, so we just looked at GPA versus IQ and ACT. What if we looked at GPA versus another pair of those predictor variables, namely, say, ACT and percentile rank? Now, we looked at the linear model for that stuff, and I think the R squared value for that was not good, right? If we, in fact, if we look back at that output for GPA versus ACT and percentile rank, we see that our R squared value is about 15%. So I expect that when I make this plot, it's going to look kind of fuzzy and sort of cloudy. I'm going to just copy the next set of of instructions that I've got there in the notes. I've written there. I've got now this open 3D command just opens a new window. Okay, it's similar to the Windows command when you're doing plots in 2 dimensions with R. And then this output WGL5, this tells me that I've now created my 5th window. Matrix, this command here, I'm just creating a matrix. It's a 2 by 2, going 1, 2, 3, 4, so that because I'm actually going to, because I'm making putting 4 things on this plot at once. One thing here, one thing there, one thing here, and one thing there. You don't see the last thing there because I didn't actually execute that. But I've got the titles of these graphs down here in the bottom. So now once you see all that, you see that I've got GPA as modeled as a function of ACT and percentile rank here, right? This is my functional model, right? Like a mathematical function. It's actually plotting, though. It's plotting the hats or the fitted values, and you see that those fitted values fall right on the where the model would be, where a plane would be. It was sort of the best fitting plane that runs right through this scatter plot. Now this scatter plot looks pretty fuzzy. It's kind of cloudy, right? Well, it doesn't matter. It doesn't matter how cloudy or fuzzy or non-linear a data set looks. You can always find a best fitting plane to it. Now our R squared value is not good. Remember, it was about 15% in this case. Again, and that sort of measures sort of the proportion of in variation in our data that's captured by our in this case, our planar model. These residuals, right, that if I could superimpose these points onto this plot over here, the sum of squared errors would be the sum of those squared residuals off the plane there. It doesn't look like this plane is coming very close to all of those points, so that that fraction SSE over the total is that's going to be pretty high. Or similarly, the regression sum of squares fraction that compared to the total sum of squares is going to be kind of low, I think. So, all right. Finally, let's take a look at what happens if we model GPA as a function of IQ and percentile rank. I'm going to just grab the next chunk of code from the notes there, and you'll see that I get this plot there, modeling GPA as a function of IQ and percentile rank in my data plot, my data scatter plot over here, and then in the plot to the right, this is my model, right? This is yeah, okay. So in this case, you can kind of see how a planar model might make some sense. It looks like if I were to drop a plane running through there, that sort of seems about right? If I sliced a plane right through, right about like that, that sort of seems like a good model. Does that sort of make some sense? Yeah, and in our R squared value was higher again for this case. I think it was 64, 65%. So that makes some sense. Okay. Now let's do all this the quote unquote long way. I'm gonna get let's get my model results the long way. I need a vector of ones that's the same length as my data set, and I'm going to c-bind that vector with all my x values, which are in, remember, if I look at my data there, my x values or my predictor variable values they're here in these last 1, 2, 3 columns. GPA was actually my response. So I want my x matrix, my data matrix, to be a matrix that I'll c-bind the ones with the data and columns 2 through 4 of that of my data set there. And of course, if I do head of x, I'll see that I've got the right kind of thing. I want my my b vector to be this. Remember, it's x transpose. This is x transpose times x, and then quantity inverse. Okay, so quantity inverse times x transpose times y. And my y values, that's these, my GPA, right? So I'll do that, and I'll get an error. Okay, so it turns out that to do these operations here, you actually need all of these things to be treated as matrices. Here's how you can check for this. You do it with the class command. I can check the class of x. Oh, it's a data frame. Okay, I can change I can force it to be a matrix if I say x is going to be as dot matrix x. Okay, so oops, x. There we go. So now if I do class of x, you'll see that it's in fact a matrix. And in fact, let me do y to be as dot matrix of data, first column of my data set there. Okay, so now if I do class of y, I'll say that it's also a matrix. Now I ought to be able to do that operation there. I'm going to change this guy to y though. This should be fine. I've got a bunch of matrices here where I'm finding the transpose of a matrix multiplied by the matrix, finding the inverse of that matrix, multiplying by matrix, multiplying by matrix. And when I do all of that, ta-da, in fact, I see here are my coefficients. If you remember your linear model, our linear model for the full model. I can get it like this, right? And compare that with I'll just type out. There we go. It's the same, right? Here's my intercept estimate, ACT slope estimate, my IQ slope estimate, and my percentile rank estimate. Okay.